Okay, we are live once again, and although we don't have anybody live in the chat room this evening, I'm going to go ahead and proceed with this evening's course. I had to cancel this session last evening, so we're going to pick it up here. This is session number 6, and in session number 6, we're going to cover topics 11 and 12, which topic 11 is your receiver. And if you remember from session 5, we covered the HF transmitter. And it's important to have a little bit of an understanding of how your equipment works. And in ham radio, um, we sometimes refer to those who don't really maintain or have an interest in the technical knowledge. We call them appliance operators. And in other words, they go out, they buy a radio, they throw up an antenna, they put this thing on the air, and that's all they want to do. I certainly hope that that's not your goal and what your modus operandi is going to be as you pursue the hobby of ham radio, but to have a little bit of an understanding. And just like the HF transmitter, the receiver goes through various stages to bring that signal to your speaker. There are various mixer circuits that take various frequencies, whether they're oscillators. We're going to cover that in the next topic, topic 12, oscillators. Whether they're oscillator circuits, phase lock loop circuits, crystal synthesis circuits, whatever, there is a mixing that goes on in both your transmitter and receiver to get the ultimate signal, the frequency that you want to transmit on, or even the frequency that you would like to receive. And the various other processes that your signal goes through, like we covered. The single sideband, which is the popular method of communications. It's an amplitude modulation signal, uh, but an AM signal, of course, is comprised of a lower sideband, an upper sideband, and a carrier. And the power that goes into that signal is kind of split up between those three elements. But your transmitter goes through a process, of course, to eliminate one of those sidebands and the carrier so that all the available power that you have in your radio gets carried out in your modulated signal, basically. And that the receiver kind of works in in the reverse. So we're going to go ahead and talk a little bit about the receiver this evening. And if you have your books handy, turn to page 111, and this is where we're going to start your receiver. One thing to note that I was kind of thinking about here, as you go through this class will become obsolete after June 30th. So as you take this course and go through it, be sure that you complete it in time to take an exam session. Look at it if you're looking at this from somewhere else in the world, across the nation, whatever. You're not local here. Check with your local club to see when they may have an exam session, and it's quite possible that they can also put together a special exam session if the date is getting close and you'd like to get licensed before the new question pool comes out. Because once this is done, the question pool will be different, although most of it will still be the same. About every 4 years, they kinda change up and, move around and do some things differently as they delete questions, they add different questions. So, you wanna make sure that you keep these dates in mind, that, you're not, going with knowledge from an obsolete question pool to an exam session that has begun putting out the exam questions with the new question pool. So keep that in mind. Okay, your receiver. We're going to get into that. There is a block diagram in your book that shows some of the elements of your receiver. Um, And receiver design has changed over the years. I don't know if anybody has played around with electronic circuits. I've played around with some of the just a very basic receiver, which literally is powered off the electromagnetic waves that it just happens to pick up in the atmosphere. And there's no other power applied to it. Of course, you have to have a little bit of a strong signal to get that. But uh, ham radio high frequencies receivers operated as a tuned radio frequency. The receiver was nice and sensitive, but it wasn't all that stable. So the modern ham radio receivers today use what's called a super heterodyne technology, which has excellent frequency stability. So the term superhet, which is short for super heterodyne, indicates a receiver with local oscillators and mixers that detect an incoming signal clean of other signals, which may be just above and below the desired signal. The stages that describe a superhet receiver are the HF oscillator, the mixer, and the detector. So kind of keep that in mind. If you look at the block diagrams there on page 111 in your book, you kind of get a little bit of an idea of what is involved in the receiver itself. And here it is in this slide. So you have your antenna, you have an RF amp. Typically, there is an RF amp, and sometimes some hams will put a preamp on the external side of their receiver, which has the ability to pick up weaker signals. But most of your receivers today are pretty sensitive. I know that my Kenwood TS520S that I had early in the early days of my ham radio hobby endeavors was a really hot receiver. In many cases, I could receive a whole lot better than I could actually transmit, but that was still a very good radio. So you have your RF amp, then you have a mixer, okay, because you have a local oscillator there in the front end of the receiver, which comes in and mixes with that signal and produces a uh, intermediate frequency, an IF signal, and goes into the IF amp, the detector, which recovers baseband signal from the IF, and it goes into the baseband amp, which literally just takes the audio and throws it into the speaker. Um, and that's the generic receiver. Then you have the dual conversion AM receivers, and you can see how different it is because it has several other stages within the receiver, the complex that is in there to give you the signal you're looking for. Okay, in any super heterodyne receiver, the incoming radio frequency is converted to an IF or intermediate frequency by means of a local oscillator and mixer. And the combination of a local oscillator and mixer is sometimes called a converter. And in your SSB or single sideband receiver, there is no difference in this regard than any other modern receiver. In a single sideband receiver section, it is the mixer that processes the signal from the RF amplifier and the local oscillator. It's taking that RF signal. The local oscillator is kind of a beat frequency type of a oscillator, which is going to extract the information it needs to send on down the line for further processing before it gets to your speaker. A product detector is necessary in order to demodulate either a CW or a single sideband signal. In an SSB receiver, it is the product detector that processes a signal from the IF amp and the BFO or beat frequency oscillator. The signal then goes on to an audio frequency amplifier. And there, from the audio frequency amplifier, it's going to eventually get into your speaker, we hope. So we remember that it's a product detector that we are concerned about in this particular question. So the term heterodyne comes from the Greek hetero, which means different, and dyne meaning to act upon or to do work. When the instantaneous voltages of two different frequency signals are multiplied, the result is two new frequencies, the sum of and the difference between the two original frequencies. Heterodyne circuits are used in most modern transmitters and receivers to convert frequencies, to perform modulation, or to perform demodulation of combinations of RF signals consisting of what is received from your antenna and what is generated inside your radio for this function. And I've mentioned earlier that there's different ways that different receivers and transmitters do this. Back in my CB days, I had an HB 525 Lafayette CB radio. It was a 23 channel radio, and it used a process of crystal synthesis, meaning that it had um, five or six crystals um, of one frequency and five or six crystals of a different frequency, all of them different, of course. And between those combinations, and depending on how your channel selector worked, it would select one side or one crystal from one side and a crystal from the other side to generate the frequency that it needed for, say, channel one or channel two or whatever. With that, when they came out with 40 channels, it was a simple matter of ordering some frequencies or some crystals rather that I could plug into inside the radio, and with a little modification and a switch and everything, I could actually add some of those extra frequencies to my transmit to my CB. And ham radio is sometimes kind of similar to that. Of course, they came out with phase lock loop, which uses a one or two crystals and plus oscillator circuits to actually generate the frequencies needed for transmitting and also for receiving. So most modern receivers are of the superhet type these days, where the incoming radio frequency and the oscillator signal are combined to produce an intermediate frequency, or an IF, in that IF stage. So when you see that word combines, think of the mixer section of a receiver stage. Um, Combining and mixing should pretty much be synonymous, particularly with this question here. And you see this block diagram of an AM broadcast receiver. Of course, your signal comes in to your mixer, and it gives you have the different uh, oscillators that produce the desired output, which is signal C. You see on the right hand side there, which is an IF, or an intermediate frequency. It goes further down the line. In strong signal areas where there may be local transmissions coming in from shortwave stations outside of the normal ham bands, interference is called image response, may develop at the sum and difference of your VFO and intermediate frequency IF signal. 13.8 megahertz minus 455 kilohertz, which is a typical IF, or local frequency within your radio, is 13.345. So you get a lower image response frequency. Um, there was an issue with one of our repeaters some years ago, in which we had a UHF frequency. We had a 2 meter repeater up, and we decided to put in a remote receiver. The transmitter of the 2 meter repeater was quite strong. However, it had difficulty receiving some of the outerlying areas, even though people could still hear the 2 meter repeater in those outlying areas. So we decided to put up a remote VHF receiver out at another location, and it was linked back to the main site of the um, standby. It was linked back to the main site through a UHF link frequency. And shortly after that was put up, we started experiencing some interference picking up a broadcast station. And it was kind of puzzling at first as to what was really happening and why we were getting, and it was always the same broadcast station. And it was just intermittent. It would be there for, maybe a few seconds and then disappear. And so, setting about looking at different um, image responses, doing some calculations, even with doing some harmonics, whether they be subharmonics or, first, second, third harmonics above that. And what it boiled down to, we even put in this 455 kilohertz frequency. And what we discovered was that cars passing in proximity of the repeater site tuned to a certain radio station where it was actually emanating a signal that was mixing with the receive side of the UHF. Now, that sounds kind of odd. I know that, but even your receiver in your car can cause some issues, and there is a little bit of a transmission outside of that because of how it mixes internally. You still have the propensity or the possibility of an actual RF signal emanating from your receiver. And this is what was happening to our repeater on the UHF frequency link. So what we did was we decided to re-coordinate that UHF frequency. And once we did that and put it on a different UHF frequency, the problem went away. So there is a little bit of that oscillation that actually does emanate, not so much as a transmission, but if it's strong enough and the uh, shielding within your the receiver is inadequate, it could very well interfere with other things. So I just thought I'd kind of throw that in there just to kind of give you an idea of what may happen in a situation, and you get an outside image response that you're not expecting. So, the new modern high frequency transceiver usually includes some type of digital signal processing. You'll see DSP, roofing filters, things of that sort. And when you read some of the advertising of some of the radios in the magazines you see today, a DSP is just a way to digitally process your signal and hopefully reduce some interference, but it allows the user to create multiple filter bandwidth settings along with a bandwidth shape for sharp cutoff or smooth cutoff response. So this wide range of filter combinations, which is all digital, really helps reduce interference under difficult conditions. Like if you're going to be on your HF radio, and it could be you might get into contesting, um, and when contests are going on, the bands tend to get really, really crowded. And if you recall, your normal single sideband signal is about 2.8 kilohertz wide. And you may hear somebody maybe 2 kilohertz away from you. And of course, they could also hear part of your signal as well. And by having some filtering and digital signal processing, you have the ability to narrow your receive bandwidth so that you can get a little bit more away from whatever the interfering signal is, from either the upper or lower side of the frequency you're operating on. Uh, some radios have the capability of shifting the IF a little bit, the intermediate frequency. And by doing that, like for instance, my Kenwood 940S has that ability, along with my ICOM 706. It has the ability to shift the IF slightly so that you can kind of tune out the interfering signal that's adjacent to you. Anyway, So, other useful functions of digital signal processing, and we'll just call it DSP, are noise reduction, notch filtering, and audio equalization and expansion. A digital signal processor, whether it's an RF, an IF, or an audio, performs its magic by first converting your analog signals into digital data. The processor performs some number crunching on that data to emulate filtering, also noise reduction, compression, expansion, or any other number of functions that the radio comes with. And some of these things are even add-ons. You'll find that some radios, when you buy them, they have just a basic DSP filtering capability, like my ICOM 706, and I can put in additional filters in there if I want, and I can select those and to get a desired amount of filtering that I need to um, get my signal to hear what I want to hear and not other stuff. At any rate, then it can reconverts the digital data back to an analog signal that the human ear can understand. So when you get to this question, all of these answers are correct in the modern DSP filter. For a number of practical reasons, DSP is usually, but not always, performed in the IF stage or stages of the receiver. Okay. If you look on page 113, there's a little Elmer hint there in that little blue box. It kind of gives you a little bit more information, kind of some of the stuff that I gave you as well. That may be helpful for you in understanding some of this. Okay, as we move along here, G4 C11, digital signal processing is found in almost all new high frequency amateur transceivers. And among many other functions, DSP helps remove noise from received signals. That's another function, not just the ability to reject adjacent channels or signals, but hopefully to kind of reduce the noise that may be on the frequency, um, even some atmospheric noise that may be there can be processed to at least try to minimize. So while DSP can do some amazing things, there are still many tasks in the ham shack that can only be done with old-fashioned hardware. And what you see here, your older HF transceivers will easily take aftermarket DSP amplified speakers that simply plug in. Now, in addition to my uh, filtering capability on my 940S, I do have a speaker that can filter additional audio frequencies in the high, mid, and low range. And there's buttons on that that can select and can even combine them. So there are some aftermarket capabilities to help with the noise situation that you might receive on the HF signals. If you look there again on page 114, um, the Elmer Point, if you start out with a used older HF radio, you can buy some of these DSP speaker systems for about 225. You can get them a little cheaper than that, possibly if you go to a ham fest or something. Maybe Amazon or eBay might have a special or something. All right, on this one, if an analog signal is converted into a digital data, mathematical operations can be applied in the time domain that ordinarily would be done in the frequency domain. So, for example, a filter's frequency response has an equivalent time response that can be mathematically tweaked using a fast Fourier transform or FFT operation. This results in much more predictable, accurate, and often amazing possibilities. Um, And after all that is done, the results are converted back to analog signals that give us the ability to hear. The input of a DSP circuit takes an analog signal, converts it to a digital signal where processing takes place, and then restores it back to an analog signal so we can hear it again. Very simple, accurate description. uh, a basic DSP block diagram is shown here where your analog signal comes in. The digital converter converts it to a digital signal. Your DSP then takes it and does its little magic and then converts it back to an analog signal. If you'll just stand by a moment, I'll be right back. Okay, I am back. I had to answer one of the students who is having trouble with the link this evening. I don't know what's going on. I've sent it 3 times now. Okay, on the front of your radio is a button marked ATT, which is an attenuator usually. When you push it in, you'll notice that the strength of the received signal drops. So, why in the world would you want to lessen the reception? Make it, harder to hear. Um, on my particular radio, on one of my radios, it's just a little dial. I can do a 10, 20, 30 dB attenuation. So, but there's an easy answer. And there are times you may not want to hear everything your radio is receiving. Especially at full sensitivity, you can receive interference from other stations on frequencies near that of the station you're listening to. So, when there's an extremely strong signal, maybe not that far off frequency from where you are, then you may want to invoke that attenuator so it will reduce overload that results from a strong incoming signal. Resend this link here. All right. So you have 40-meter privileges, and they're shared with foreign broadcast stations. From early evening to a couple of hours after sunup, you'll hear some rather interesting full carrier, double sideband AM shortwave stations coming from far east or far west. We can sometimes dodge the interference thanks to the HF transceiver's notch filter. And you'll find this on many of the modern receivers. They'll have the ability to notch out certain frequencies. So the notch filter may be varied to reject a specific frequency, such as a whistle coming in from these faraway shortwave stations. And it just takes a little bit of careful adjustment, and that interference may disappear. Newer transceivers may incorporate automatic notch filters that use DSP, which are capable of notching out several interfering frequencies. Hey, hi, Cohen. How are you?
Doing well.
I don't know what was going on with the link. I sent it out 3 times. So, but at any rate, I decided it's just me here, so you're joining me, and, I just decided to go ahead and run with it so you can pick up on it a little bit later on.
Okay.
Alright, sounds good. I'm gonna try to mute you here. I can't mute you, you'll have to do it on your end. I don't know why I've lost the ability to mute now.
And well, before my screen wasn't working, my camera
Yeah.
or my mic, so we'll just do that.
I'll let you mute it then. Very good, thank you. Yeah, it won't be difficult to catch up, so, I'm not that far into it, we're just talking about the receiver right now. But, glad you were able to join me live. I'm, moving right along from this one. The, new ham gear incorporates a circuit called ANF on the front panel, and this is an automatic notch filter. We're going to play off the previous slide, and it's handy on 40 meters where there is a lot of foreign broadcast carrier noise that will drive you crazy uh, without the automatic notch filter or ANF. ANF uses DSP technology to magically eliminate the noise. Now, when I first got into the hobby, there were quite a number of 40 meter AM shortwave broadcast stations. Uh, they mostly occupied the portion of 40 meters for as far as our ham frequency capabilities here in region 2, just really above 7.1 megahertz and all the way outside the 7.3, which is our limit. And when I was a general class licensee, trying to use voice on 40 meters as evening approached and into the night was just about virtually impossible, except for the strongest of ham radio signals. And my radio didn't really have the capability to properly notch all that out. But at any rate, 40 meters was not really one of my favorite frequencies. It's a little better these days. The other regions through the International Telecommunications Union has has worked to predominantly minimize AM stations in region 2 40 meter band. Some of these other regions don't have the full 7.0 up to 7.3 megahertz like we do here in region 2. Um, but at any rate, 40 meters is a lot more friendly these days with less AM shortwave stations. And honestly, a lot of the shortwave stations are kind of going by the wayside these days. I don't know if it's because, not many people are listening to them. I like to listen to shortwave radio stations. And if you have one of the newer transceivers these days, most of the receivers are pretty much general coverage. So you have the ability to hear everything across the entire spectrum, from below the 160 meter band up to above the 10-meter band. And you can find some interesting stuff on there, definitely in the shortwave. I like to get I like to get some of my news from some of the foreign broadcast stations because they seem to be able to tell the truth about what's really going on in our nation. They seem to understand it better than our own media here in the States. So I like to get a little bit of news from outside on the shortwave broadcast. In a frequency modulation receiver, things are processed a little bit differently. Signals coming from the intermediate frequency amplifier are fed into a discriminator, which acts as a frequency to voltage conversion stage, sending the resulting decoded signal onto the audio amplifier. And the discriminator is just really a very simple circuit, and It contains maybe a Zener diode or something of that sort to help with the filtering to pick up the frequency modulated signal. You can look up online what an actual discriminator circuit looks like. If you have a radio with an FM schematic diagram, you can go in and look at the schematic diagram of your manual, and you can see where all that is as well. And a lot of the schematic diagrams that come with um, your radios, presuming your manual has that in it, used to be most of the radios that I've seen do contain a schematic diagram of your radio, typically in the back, and some of it's fold out pages. But even if it doesn't, you can get a service manual for your radio, and they definitely have schematic diagrams. And these schematic diagrams, you'll notice that in some of the stages there, there's little blocks that are dotted lines, and the dotted lines basically would represent what you would see as part of a block diagram. The block diagram is not a schematic, but a block diagram kind of gives you just an overview of what's in um, your radio, your transmitter, your receiver, or whatever. And those block diagrams can correspond to those little dotted line blocks of the actual schematic. All right. The S meter on your transceiver ties directly into the receiver section of the radio. We kind of covered this a little bit before as far as, decibels and gain and things of that sort. Um, so it's tied into the receiver's automatic gain control, which is part of your signal strength circuitry. So most of your HF transceivers, there is a front panel setting for the receiver AGC. Set it at automatic or slow when copying single sideband voice emissions. But if you're doing CW, you want to set this to fast. And the automatic gain control, if you remember, predominantly works to make sure that what you're hearing isn't, fading in and out, that it maintains some type of consistency in regards to the level of the signal that you're hearing. So set it for slow for single sideband, set it for fast for CW. If the AGC, however, is turned off, the S meter will not budge. So leave it on slow or automatic or one of those. High frequency ham transceivers all incorporate an S meter. S meters measured received signal strength. Uh, the S meter can be used to determine if your antenna system is working properly. The A lot of the newer radios, the meters are kind of a multi-purpose. You may have a switch on there that allows you to see plate current, allows you to see what the SWR might be, um, the signal level, the power output. So there may be a multiple functions for your meter on your radio. Excuse me. On 40 meters, you should see approximately S2 indication of normal background noise, and that's about right. If you're listening to 40 meters, you can expect to hear about an S2 noise level on any typical day. Um, Sometimes this can be much more, and I've seen noise levels as high as S9, S8, S9 on my meter, and only the strongest signals are going to get through. Um, if you see a higher reading of background noise, it's an indication that uh, if you see a higher reading of background noise, this is an indication that your antenna is performing properly. Huh? Well, I don't know. However, if your S meter doesn't budge on 40 meter noise, something is probably wrong with your antenna system. I'm not so sure that if you see a higher one, Yeah, you're actually receiving. That just means your antenna is receiving okay, but you may be receiving just higher atmospheric noise because the atmosphere is just noisy for some reason. Okay, I'm going to get into the questions now. So, the simplest combination of stages that implement a superhet receiver, and again, this is very basic. Remember, if you think back, there is an oscillator circuit, mixer circuit, and a detector circuit. So C is your correct answer for this, for just a separate superhet receiver. The circuit used to process signals from the RF amplifier and local oscillator then send the result to the IF filter in a separate super heterodyne receiver. Again, this is taking a local oscillator and putting it with this RF signal and doing a mixing process is called the mixer, C. So what circuit is used to combine signals from the IF amplifier and the BFO, or the beat frequency oscillator, and send the result to the AF amplifier in the single sideband receiver? Remember, we wanted to kind of remember this word detector. So it's the product detector. Your answer is D there. What is another term for the mixing of two RF signals? Remember, we got into that explanation of Latin of what hetero and dining or dine means, and it's not anything sexual or anything. But the heterodyning is what the term is for mixing the two RF signals. What receiver stage combines a 14.250 megahertz input signal with a 13.795 megahertz oscillator signal to produce a 455 kilohertz IF, or intermediate frequency? Simple stuff. Again, you're taking two frequencies and you're doing something with them, and it's called mixing. So it's the mixer. If a receiver mixes a 13.8 megahertz VFO with a 14.255 megahertz received signal to produce a 455 kilohertz intermediate frequency, or IF signal, what type of interference will a 13.345 megahertz signal produce in the receiver? And I went through that little explanation of what was happening with our repeater and everything. And that term is basically image response. So B is what's happening there, your image response. Which of the following is an advantage of a receiver DSP-IF filter as compared to an analog filter? The following an advantage of a receiver DSP-IF filter. Um, should be pretty easy because B is wrong. It doesn't mean fewer digital components are required or that mixing products are greatly reduced, um, or that even the DSP filter is much more effective at VHF frequencies. So those B, C, and D are ridiculous answers in my opinion. So the only thing that really makes sense is you get a wide range of filter bandwidths and shapes that can be created. That's your advantage of your DSP IF receive filter. Which of the following is needed for a digital signal processor IF filter? Okay, remember what it does uh, when you're doing signal processing. And the key here is digital signal processing. So within that, you have an analog to digital converter. You also have a digital to analog converter. It's got to you come in with the analog to digital, it gets processed, and then somewhere along the line, it has to take that digital and convert it back to analog so that you can hear it in the speaker. And you have to have a digital processor chip, obviously. So all these choices are correct. So which of the following is a function of a DSP? Which of the following is a function of the DSP? Oh, grounding is stupid. It doesn't increase your antenna gain or your antenna bandwidth. So the simple answer here that it makes sense is to remove noise from the received signals. How is DSP filtering accomplished? I don't recall talking anything about phasing or spurious phasing or anything, D possibly, but your correct answer here is what it does is it takes the processing is accomplished by converting the signal from analog to digital and then using DSP and then converting it back to analog. So B is your correct answer here. What is the one reason to use the attenuator function that is present on many HF transceivers? Remember, you want to attenuate signals that could be very strong, overloading your front end on your receiver. So basically, it does it works to reduce the signal overload due to strong incoming signals. What is the purpose of the notch filter found on many HF transceivers? Uh, Notch does exactly what it says. You take a little notch, it's looking at a specific point, and it's taking care of that. It's filtering out a particular, um, basically a particular passband or a frequency or a segment of the band there. So it reduces the interference from carriers in the receiver passband. And which of the following can perform automatic notching of interfering carriers? Again, that's the part of your DSP filter function. B. What type of circuit is used in many FM receivers to convert signals coming from the IF amplifier to the audio? Um, we're talking specifically of FM right now. And what it has to do is it needs to, pick out the signal properly. So it uses a thing called discriminator. It uses a circuit called a discriminator circuit in there. Where is an S meter found? Well, your S meter is going to be found in the receiver, of course. That's what we're talking about. So that's where your S meter is found typically. The S meter's function is specific to the receiver. And I know I mentioned things about a lot of these meters have a multiple function and you have a switch and everything, but the S meter specifically is a receiver function. And although you have the ability on many transceivers to check your SWR, your power output, things like that, of course, your power output uh, meter is tied to your transmitter. So S meter is a receiver. And what does the S meter measure? Easy stuff here. It checks your received signal strength. So now that we've done that, um, I'm going to go ahead and we're about an hour here. Um, I'm not so sure if I'm really going to be able to cover topic 12. Um, Topic 12 is 60 slides. I think we can actually fit it in there. Uh, we'll kind of work on it a little bit. And while my PowerPoint presentation is not responding, um, if you need to ask questions, need some clarification, look in your book or drop me an email, Wayne at n3lms.net. We're going to talk about oscillators and components here, I think. If I got the right PowerPoint. Yes, I do. Okay, close that one out. Get my slideshow going again. Get my cue card over here so that I can quickly access it. All righty. Oscillators and components in your book begin on page 119. 119. Yep. This should go fairly quick. I don't think we'll have any problems getting through it. We'll spend about a minute on each slide, I guess. Anyway, oscillators are very important to your transmitter and receiver, and they are the primary signal creators in all that we do. So an oscillator is really an amplifier with positive feedback. We're going to see a diagram here in just a moment. It also has a tuned circuit to set its frequency of oscillation, but some of them will also employ a phase shift network or other filter. So in order for an oscillator to sustain oscillation, the total gain must be greater than unity at the frequency of oscillation. To keep that oscillator in motion, a tuned circuit at one specific frequency will provide the necessary positive feedback loop. Um, okay, just like keeping grandpa swinging back and forth on his senior citizen swing. I don't know where they come up with this stuff. So, oscillator is an amplifier with positive feedback, and it contains circuitry for a positive feedback loop. And here is a circuit diagram. This is also on page 119. So your oscillator circuit comes in, you get your signal in there, and then of course on the output there's a positive feedback, and it produces an oscillation, and then you get a waveform out there. Some of these are going to be a sine wave oscillator, you're going to get a square wave oscillator, or a sawtooth wave oscillator. But this is the very basic description of an oscillator with a feedback or a loop back component um, to maintain a certain oscillation. The symbol used to denote inductance is L and capacitance is C. And an oscillator circuit really contains an LC network. It involves inductance and capacitance. The LC oscillator is found in the radio frequency circuits of your HF transceiver. It consists of a tune inductance and capacitance resonance circuit found in the tank circuit of the radio. And sometimes these do get out of tune. Maybe the crystal, as it ages, it might drift a little bit, and so the inductors and the capacitors have adjustment capability to allow you to retune to get kind of back on frequency. Your dial may be a little bit off, and sometimes these circuits can be tuned to basically put your radio transmitter and receiver back into proper alignment. In the triode vacuum tube, the control grid acts like a variable valve. As a matter of fact, tubes used to be called valves. If you hear an old timer, somebody that's like 150 years old, talk about a valve in a radio, they're talking about a vacuum tube. So it regulates the flow of electrons between the cathode and plate. The hint here is the control grid is regulate equals control. So if you want to regulate something, you want to control it. And the triode vacuum tube, there is a control grid that acts like a valve. Do we use tubes today? I'll tell you this, there's still lots of really good radios out there that are still quite usable, that are tube rigs. Most of the time, you'll find them as hybrid rigs, like the Kenwood TS520S, for instance, is a hybrid. It uses a lot of electronic components on the front end of the radio, but in the final output, it uses tubes. It has a smaller tube for the driver circuit, and then it uses two other tubes for the final output power. Typically, 12YB 7s are a typical driver type tube, and 6146Bs are a typical power output tube. It gives you 100 watts. If you buy an amplifier, doesn't matter how powerful it is. I have an Ameritron 600 amp um, amplifier in my desk here. It uses 3 vacuum tubes to generate 600 watts. They are quite efficient, much more efficient than many of these power transistors. So you may run across a rig that has tubes in it, and it's good to know a little bit about what some of the components, the internal components of a vacuum tube happen to be. So, yes, as I was just explaining, there are some vacuum tubes. The tetrode tube uses an anode, cathode, and screen grid that reduces grid to plate capacitance. So, this collects secondary emissions from the plate, which will slightly increase screen grid current. So, screen grid reduces grid to plate capacitance. FETs, field effect transistors, they have a high input impedance, and they have a gate, drain, and source. They're a little different than your standard transistors, which have different names for the components of them. In an FET, those components are called a gate, drain, and source. You have a collector, base, and emitter in a standard transistor. But the gate does exactly what the name implies. It controls the grid of a tube with the gate generating an electric field that increases or decreases the amount of current flow. You have to be careful where you place power supplies. Uh, the type of power supplies we're talking about are the ones that you plug into the wall and you get 12, 13, 14 volts out of it. Your older transformer type power supplies mount their transistors on the large heat sinks that are exposed to open air. And if the supply's power transistor is accidentally pushed up against something else that is ground, you will short out the collector voltage and likely destroy the power transistor. So you just got to be very careful of where you actually put that. You also want to make sure that there's plenty of airflow because those transistors could get very hot and they need to be cooled down. Uh, and it'll extend their life if they don't run too hot. Bipolar transistors, uh, they can saturate fairly easy, and when they do, the collector and emitter base junctions are forward biased. So when the bipolar transistor is used as a switch in a logic circuit, an extremely small change in the collector base voltage will cause a large change in the collector current, allowing the transistor to switch between cutoff and saturation within the collector current specifications to keep the transistor from self-destructing. So it is in this saturation and cutoff region that the transistor will act like a switch. We find the MOSFET transistor in the front end of the modern HF transceiver. The MOSFET is a metal oxide semiconductor field effect transistor in which the gate is separated from the channel with an extremely thin insulating layer. It's a MOSFET has a gate which is separated from the channel with an extremely thin insulating layer. So, because of that, manufacturers usually install a gate protective Zener diode, which prevents the gate insulation from being punctured by small static charges or excessive voltages from an event like a nearby lightning strike. I've had I've had near lightning strikes here, and fortunately, I've had things um, available to me to kind of protect my equipment. Fuses on my uh, telephone line coming in um, was one thing. Your power strip can protect some of your equipment. I had a small Dentron Junior tuner between my antenna and my transceiver, which basically took the near lightning strike. It wasn't a direct, it was near proximity, and it took out a little cheap Dentron Junior tuner. No big loss, but it protected my equipment. The germanium diode is sometimes found in the detector stage of a receiver. Their low forward voltage drop is minimal, and the approximate junction threshold voltage of this diode is zero point 0.3 volts. So these signal diodes are sensitive and can burn out if you accidentally overheat them while soldering them in a replacement scenario. Germanium diodes, and they're almost like a little glass one, I think, in some cases. But they have a junction threshold voltage of a mere zero point 0.3 volts. Here in this diagram, it's also in your book, I do believe, on page 122. You can see a little bit more information, a little bit more clearly than you can probably see this slide. But there's an array of LEDs on the left, and there are, of course, bias resistors mounted on a printed circuit board. And this kind of gives you a little idea of um, how those LEDs or light emitting diodes function. And that's, in the earlier days of digital clock readouts and everything, they were made up of 7-segment LED displays. You can see that at the bottom of your diagram there. And they were turned on and off accordingly. The circuitry within would actually make them light to give you the correct time readout. All right, silicone diodes. There's what a silicone diode typically looks like. They're rectifiers, and they're usually found in the rectifier section of your transceiver's power supply. In this case, what we're looking at here in these four is most likely a full wave bridge rectifier. If you remember some electronics and components that we did earlier, we were just kind of repeating this. A full wave bridge rectifier will take that AC signal and turn it into a nice, almost smooth, direct current or a DC signal, uh, a DC voltage. Of course, other filtering is in there. You might have a filtering capacitor or two and some other components. But the silicone diode does offer stable operation at high temperatures. So a junction threshold voltage of about zero point 0.7 volts, high reverse resistance, and they have long-term reliability. You can bet that when you see a quartet of large silicone diodes in close proximity, they are the main ingredients of a full wave bridge rectifier. Yeehaw. The Schottky diode is a fast switching point contact diode with lower capacitance, offering faster switching capability. Hold on. And those Schottkys have the ability to switch much faster than a standard silicone diode. You might find the Schottky diodes in what's called a crowbar circuit um, for a power supply. And the crowbar circuit, basically, what it does is it kind of protects your power supply from voltage surges or reverse connections or some other thing. But it's an important consideration in HF transceivers for handling many digital modes where fast switching time between transmit and receive is required. So that would be in there to switch from your transmit to your receive, um, and it offers lower capacitance as being an advantage of the Schottky diode over a common silicone diode. That is what we want to take away from this particular slide. The Schottky diode offers lower capacitance as well as faster switching time. Incandescent lamps. Well, they're becoming almost a thing of the past. Progress marches on, and most of your small lamps in the ham shack have been replaced with LEDs, light emitting diodes. My sub display of my Kenwood 940S had really wee small incandescent lamps, and they all burn out about the same time. But a friend of mine was checking something else out, and he took it upon himself to replace those little incandescent lamps with little LEDs. That I should never have another problem with my sub display ever going dark again. So LEDs have an advantage of nearly infinite life, low power consumption, and nearly instantaneous response time. LEDs are becoming the big thing now instead of the um, what do they call them, the fluorescent type light bulbs nowadays. Of course, when the government decided that we weren't going to be allowed to use incandescent lamps anymore, I stocked up with several cases of incandescent lamps of different wattages, 60s, 100s, 40s. You name it, I got them. That's not the end of incandescent lights, however. The one thing that is not affected by that is the heavy duty or rough duty type applications where you can still get um, incandescent light bulbs. They're just a little bit more expensive, not as expensive as the CFLs, your compact fluorescent lights. Definitely not as expensive as LED lights these days. However, LEDs are the going thing. And I kind of thought this a long time ago. I said, I wish we could light our homes with LEDs because they virtually almost last almost forever. And I like LEDs. I do have some LED lights around here. As a matter of fact, in my shack here, I went out and bought a strip of lights, LEDs, and to provide extra lighting in here, and it was adhesive backed, and I just put it right along the edge of my shelf. I have a little switch for it, and I really like them. They give me the light I need here in my shack in my little studio. Um, but they do last quite a long time. So they do. One thing to kind of keep in mind, however, is that in poorly designed and poorly manufactured LED lighting might cause some interference on your radio. They can be a little bit noisy. I have one particular light over one of my counters in my kitchen that will cause noise on my VHF radio when I turn it on. So something just to be aware of. Oops, where am I? Boy, that's something I did there. All right. Not all your semiconductors are based on silicon. There are many exotic materials that function as semiconductors and do more than your garden variety diode or transistor. And one of the first light emitting semiconductor materials was the gallium arsenide phosphide, or the GaAsP. GASP is what they really called it. So while an LED has two terminals and conducts better in one direction than the other, its similarity to a normal diode really ends there. So many of your more exotic materials have been discovered and exploited for the manufacture of LEDs, particularly when it comes to the bright LEDs these days. The light emitting diode is always forward biased when it is emitting light. Current only passes in one direction in a light emitting diode. If you remember, a diode only passes current in one direction and blocks it in the other. So it's very important that when hooking up your light emitting diodes, that they're properly configured so that if you want them to work properly, the current is going to flow properly through it. Um, when the current is passed through the PN junction, it's forward biased, and the light emitting diode almost instantly turns on. Liquid crystal compounds were discovered in the late 1800s, and of course, nobody knew what to do with them, not even the hams. So your LCD employs one or more hundreds of possible substances that change optical properties when exposed to an electrical field. Liquid crystals produce no light of their own, but can alter either the reflection or transmission of light in accordance with their electrical stimulation. A transmissive LCD display needs some source of backlighting. So while a reflective LCD does not. Like the LED, the LCD technology has evolved tremendously in recent years, making ham radios and other electronic gadgets just a lot more fun to look at. And if you remember, some of the TVs that when all this was coming around, they came out with LCD and then a combination of LCD and LED. And your liquid crystal displays kind of evolved a little bit and were mixed. So many of your new high frequency transceivers use a liquid crystal display, which requires backlighting at night. The monochrome black and white liquid crystal displays achieve their own brilliance out in the sunshine. Color LCDs, however, have dramatically improved visibility in direct sunlight. With backlighting, the color LCD looks terrific. Thanks to microprocessors, your new general class high frequency transceiver works much like a miniature computer with everything on a single integrated chip. So much capability packed into such a small component. And that's very true. I mean, you look at some of the HF radios that are out there and available today. I mean, it's amazing um, that my ICOM IC706 is as small as it is, and I have all of my HF frequencies. And not only that, I've got 6 meters, 2 meters, and 70 centimeters on it. And it's all packed into a nice, neat little package. And the other advantage that it gives me is that I don't have to mount this radio on my dash or under my dash or in a way. I can put that radio under a seat and I have a little cable that runs to the remotable control head that sits right at eye level, right above my steering wheel. And while I'm driving down the road, I don't have to take my eyes off the road at all. I can sit there with my hand on the steering wheel and use one finger and run that dial around and around and around until I hear something that I want to listen to or even communicate with. So, yeah, there's a lot of features packed into that little tiny radio, and it's just amazing. The monolithic microwave integrated circuit, MMIC, is a favorite among microwave operators up on 10 gigahertz. So they're talking about the X band, and they use MMICs in the microwave equipment as fixed gain amplifiers with excellent signal to noise ratios. So the monolithic microwave integrated circuit, MMIC, operates in your X band. We nickname the op amps or operational amplifiers an op amp. Getting ahead of myself here. It's an analog integrated circuit device, and the op amp offers high gain over a large range of input frequencies and is direct coupled differential amplifier whose characteristics are determined by components external to the amplifier unit. Your op amp is an analog device. Your analog circuits offer a smooth ride down grandpa's old house banister. I don't know where he comes up with this stuff. Digital circuits are like bumping down individual steps, and that's true. If you actually looked at a digital waveform, you would see that it's not smooth. Um, we find digital circuits in frequency counters, NAND gates, and microprocessors. Kind of think about this a little bit. Today we have MP3s and things of that sort that we listen to our music on and things of that sort. And while A digital signal, I mean, an MP3 is actually a digital signal, and while it can approximate the sound of an analog signal, it is not an analog signal at all. There is a definitive difference. If you took a vinyl record and you played that vinyl record, of course, everybody remembers the stylus and the needle and everything and how that sounded while you were playing it. You hear that little initial static, and then the song comes on. You're not hearing the static when the song is playing, but you're hearing an exact reproduction of what was recorded on that vinyl disc. And you can take and record that off onto create an MP3 file. And while it is very approximate and very close to the analog signal you just listened to on that vinyl, it is not an exact reproduction. Any rate, getting back to this, inside your new HF transceiver will be an analog linear voltage regulator regulating current to keep the desired voltage steady and within specifications. Well, your HF frequency, your HF transceivers, there are numerous circuits, and boy, I don't know. We need to review a little Boolean algebra. Um, yeah, that's quite the class if you want. But there's a binary number 0 could result in a little handheld radio's LCD display showing a blank off segment. The binary number 1 may tell the LCD display to turn a segment on. The reason your LCD handheld display draws such little current is that once each segment gets its command to be either off or a 0 state or on or a 1 state, it remains that way until it receives another binary command. Boolean algebra is used in many digital circuits. So they're logic circuits, basically, is what they are. And your new HF transceiver, they provide command paths from one stage to another. Logic symbols give us a clue about what it takes to trigger the next on or off sequence, and sometimes reversing them. What is really required are truth tables to program multiple inputs and have a single output logic path. And the most basic form of using the binary system for the processing of digital signals will lead to binary zeros triggering an off state and a binary 1 triggering an on state. The only thing you really need to remember here, and I tell you, we could get into this, we could talk about AND gates, NAND gates, OR gates, NOR gates, and all kinds of other stuff. But basically, what you really want to remember here is that in binary, ones and zeros represent ons and offs. A 1 is on, a 0 state is off. In a shift register passes the flip-flop data up or down to each other rather than just an output. Parallel data may be converted to serial data or the reversed through a shift register. Just remember that your shift register passes your data up or down. Boy, we got a lot of information here, don't we? There's a lot to read here, and really, I don't think I really want to go into all of this. It's pretty easy to look at because you have TTL logic circuits. You've got you know FET transistors and CMOS and stuff like that. Um, One thing to note, however, is like the third sentence down, the truth tables. Let me just kind of point to it right here, right here. Do. The truth tables for TTL and CMOS are identical, but there are some practical differences. TTL is very fast, but it's also subject to noise, which can result in false triggering. Um, in addition, it can use considerable power in high density circuits, whereas CMOS is more immune to noise and uses considerably less power but there's a trade-off there as far as speed and how it operates. So when engineers are selecting circuits, they have to remember whether they need some fast or slower processing. Let's kind of skip right on down here to the very bottom. Um, the big advantage of CMOS logic over TTL is that CMOS offers lower power consumption. And that's all you really need to know. A CMOS is lower power consumption. So many of your transceivers have a read-only memory or a ROM in there. It is pre-programmed at the factory to set band limits and tuning ranges and many other functions that define your radio. This read-only memory, hold on a second. Okay, what I really need to do here is I need to set my ringer all the way down. All right, my ringer is off now. So sorry about the interference. Any rate, getting back to this, the ROM in there in your transceiver sets certain band limits, particularly on transmit, tuning ranges, and many other functions that define your radio. The read-only memory is permanent and does not need a backup battery. An EEPROM would have your memory circuits. It's an erasable, programmable read-only memory. It doesn't need a battery backup. Once you program in your memory channels and everything, they pretty much stay there. You don't need to keep power on it. And non-volatile memory is what we see in newer transceivers. And even though you pull the plug, information remains in memory, even though there may not be a built-in battery backup. That would be your ROM or EEPROM. Digital logic circuits. They can be explained by some simple grammatical statements. So there's some basic decision-making element of digital logic circuits. An AND gate, for instance, has, as the name suggests, gives an answer C if A and B are true. I think in your book, if you look in here, I do believe it shows what some of these circuits look like. Let me look and see here. I think it does. I can't be on page 128. There's a truth table. It kind of shows the AND circuit. If I can pull up, let me see if I can actually get. I'm going to pull up this image of an AND circuit here. Okay. That's not a very good one. Give me just a moment here to. Wow. They keep going dark on me. Just give me a moment. I have this somewhere on my computer, but I don't have time to look for it. But I want to kind of give you a little bit of a view of what these circuits actually look like. Man, I don't know why they're like this. Save image to my desktop. All right, here we go. I'll bring this up. This is what the logic circuits actually look like. You have your AND, your NAND, your not, your or, your nor, your or, and nor. And there are certain aspects of it. Um, in that logic table, it kind of gives you some information about how it works. So, in other words, what they're saying here is see if A and B are true. Where is it? Where is it at again? Okay. A and B are true. Okay. If there's a 1 and a 1, and since this is an AND circuit, it's actually combining both of these have to be positive for there to be a positive output or a 1 output on this. And that's what this is saying right here. So if we use 1 to represent a true condition and 0 to represent a false condition, we easily describe the behavior of the gate. C will only be true if A and B are true together. Um, or C is a 1 if and only if A and B are 1. So the behavior of any type of gate is defined by that truth table on page 128 there. There are 5 basic types of combinational logic circuits Dan, I just showed those to you. So if we look at the truth table down at the last bottom of the page there, if we look at the truth table, an AND gate will only give us a high output when both inputs are high. So now they ask about the NOR gate. The 2-input NOR gate will give us a low output when either or both inputs are high. In other words, if you it's just the opposite of an OR gate, really, and an AND gate. A NOR gate, if both inputs are low, uh, the output will be high. If both inputs are high, the output will be low. That's what a NOR gate is, not either or. An OR gate, if you took an OR gate like we saw earlier, the OR gate, if one input was high, either one, either A or either B, the output would be high. If neither input is high uh, on an OR gate, not the NOR, on the OR gate, if neither input is high, the output is not high as well. The NOR gate works a little bit opposite of that. So just remember a NOR gate, the low output when either inputs are high or both are high. Flip-flop circuits require 2 input pulses to generate 1 output pulse. Each time you add another flip-flop, you multiply the number of inputs required to generate 1 output by a factor of 2. 2 times 2 times 2 equals 8. In short, being base 2, 3-bit, or t to the third power equals 8. Whoa, look at this. Complex digital circuitry are called microcontrollers. So here is a picture of a large scale integrated mounted on a printed circuit board, large scale integrated circuit mounted on a printed circuit board. That would be your processor, and it probably contains a whole lot of uh, complex circuitry to give you all the features that you need in your radio or computer or whatever. Oh, there we go. Let you kind of mull that over a little bit. Give me just a moment. Okay. We're going to get into the Q&A now. All right. So what are the basic components of virtually all sine wave oscillators? You have some basic components of a sine wave oscillator. And that word divider doesn't fit. Multiplier and mixer, it doesn't fit either. Feed forward loop, I don't know what that is. Your only logical answer here is a filter and an amplifier operating in a feedback loop. If you remember that picture, get that visual in your head. It is a filter and an amplifier operating in a feedback loop. That is a basic, simple sine wave oscillator. So what determines the frequency of an LC oscillator? Remember what L and C really stand for. L stands for inductance, C for capacitance. So by knowing that, you automatically know that your answer is going to be C, if I can get it to work here. The inductance and capacitance in a tank circuit. Now stand by just a moment. Moving right along here. Which element of a triode vacuum tube is used to regulate the flow of electrons between cathode and plate? Remember that thing that you need to regulate, you need to control it. So it's usually the control grid that controls the flow of electrons. What is the primary purpose of a screen grid in a vacuum tube? Um, Again, this is your screen grid has a specific function in that it wants to reduce your grid to plate capacitance. It's a screen. Think of that as, between the grid and plate, there's a certain distance there that creates a capacitance. If you remember what a capacitor looks like, it's two plates uh, that predominantly hold a minimal charge within them. So if you understand and have a visual of what a capacitor is, and you think about this screen grid as being something that goes between that grid and that plate, it is to help reduce the grid to plate capacitance. Which of the following solid state devices is most like a vacuum tube in its general operating characteristics? Um, we talked a little bit about this. The FET, or the Field Effect Transistor, operates more like a vacuum tube than it does a regular transistor. Why must the cases of some large power transistors be insulated from ground? Mostly because your collector and your drain are exposed. You don't want to get those shorted against anything. So you want to avoid shorting the collector or drain voltage to ground. What are the stable operating points for a bipolar transistor used as a switch in a logic circuit? Remember, we were talking a little bit about saturation and cutoff. So it's the saturation and cutoff regions. Your answer is A on this. Which of the following describes the construction of a MOSFET? Um, Kind of think back a little bit uh, about this. Um, the gate, it has to do with the gate, and it is separated from the channel with a very thin insulating layer. And that's one of the following descriptions of the construction of a MOSFET. What is the approximate junction threshold voltage of a germanium diode? Germanium diode, it looks like a little tiny glass diode, and typically it's about 0.3 volts. Your answer is B. And if you get into a silicone diode, it's a little bit different. So the approximate junction threshold voltage of a conventional silicone diode is about zero point 0.7 volts. Your answer is C. Which of the following is an advantage using a Schottky diode in an RF switching circuit rather than a standard silicone diode? Think about that Schottky diode a little bit more in terms of capacitance because it has a lower capacitance than a standard silicone diode as far as being in an RF switching circuit. So it's going to be least likely to affect your RF circuit um, than a silicone diode would. Which of the following is an advantage of an LED indicator compared to an incandescent indicator? Boy, I tell you, we love those LEDs, I think. They are lower power consumption. I tell you, you can get these LED light bulbs these days. Man, they hardly take any power whatsoever off of your 110 volts. So they have a lower power consumption. There's a faster response time as compared to a CFL even, and they have a longer life. So all of these choices are correct. D. How is an LED biased when emitting light? Remember, in order for it to actually emit light, it has to have the current flowing in the proper direction. So it's forward biased, and that's when it emits the light. Which of the following is a characteristic of a liquid crystal display or an LCD? The characteristic, of course, if you remember, the LCD requires some type of ambient or backlighting because it does not emit any light of its own. So A is your correct answer here. What is a microprocessor? Remember, that's a kind of a you know a complex component, but really it's a computer. The simplest um, description of it is being B, a computer on a single integrated circuit, ever how complex it may be. What is meant by the term MMIC? Um, again, think about microwave. When you think of MMIC, think about microwave. You'll get this answer almost. There's no doubt you get this answer correct. B, it's a monolithic microwave integrated circuit. What kind of device is an integrated circuit? Operational amplifier. What kind of device? Your choices there are digital MMIC, programmable, and analog. Think about that op amp. We're not talking about something that's in the microwave region. We're not talking about programmable logic. We're also not even talking about digital. D, analog. It's the kind of device it is. Your integrated circuit op amp is just a simple analog device. Which of the following is an analog integrated circuit? And you look down those things, it can't be NAND gate. That's a logic circuit, although it is part of an integrated circuit. The microprocessor um, is a digital, typically a digital processor type thing, and NAND gates are digital as well. Frequency counters are digital. The only logical answer here is linear voltage regulator. That is an analog integrated circuit. Which of the following is an advantage of using the binary system when processing digital signals? Okay. Remember what we talked about binary. Binary means two different states. So when you're thinking about binary, the two states that you have available are either on or off or ones and zeros. A is your correct answer for this. What is a shift register? Okay. Remember what the shift register does. It's a clocked array of circuits that passes data in steps along the array. Uh, Whatever state it is, you can shift it using this type of circuit, and it's called a shift register. Which of the following is an advantage of CMOS integrated circuits compared to TTL integrated circuits? The only thing you really need to remember about the CMOS is that it has a lower power consumption. A is your answer here. What is meant by the term ROM? Remember, ROM, you can't do anything with it. It's already programmed. You can't change it in any way. It is a read-only memory. What is meant with when memory is characterized as non-volatile? Remember that being non-volatile means it doesn't need any external power to maintain what information is stored in it. So C, the stored information is maintained even if power is removed. Which of the following describes the function of a two-input AND gate? Remember what the AND gate does. It it has to have an input and another input in order to get a particular output. So when you look at your answers here, the output is high only when both inputs are high. You have to be very careful on this one because if you could get very confused on it. But think of I have to have this and this in order for this to be such. The NOR gate. Okay, I kind of touched on and explained a little bit about what an OR gate does, but the NOR gate is kind of an opposite of that. So when you look at these descriptions that are available here, these choices, your NOR gate, the only logical answer to this is the output is low when either or both inputs are high. Um, the OR gate being either or. The OR gate, if input 1 is high, then the output's going to be high. If input 2 is high, then the output's going to be high. If both of them are high, the output's going to be high. If both of them are low, the output's going to be low. The NOR gate is the opposite of an OR gate. So if you understand the OR gate and you know what the NOR gate, then you can understand what the NOR gate does. So if either input is high or both inputs are high, the output is just the opposite. It is low on a NOR gate. C is your answer on this, by the way. How many states does a 3-bit binary counter have? How many states does a 3-bit binary counter have? Okay, we're talking about a binary counter here, and it's a 3-bit binary counter. Remember, kind of visualize what was in the book there, where it went 2 times 2 times 2. Your answer is 8. That's how many states your 3-bit binary counter has. Complex digital circuitry can often be replaced by what type of integrated circuit? Very easy here. A microcontroller. Complex digital circuitry. And what they're talking about here is that you have a whole lot of different components in this circuit, and instead of having them individual circuits, and it's very complex, they combine them all into one little nice, neat little package called a microcontroller. So that's the end of our slideshow for this evening, and pretty much the end of our session. If my one online active student is here. If he has any questions or any comments, I'll be more than glad to answer them before we stop the broadcast. Anything you got there, Cohen? Did I confuse you enough tonight?
No, actually, believe it or not, this section was pretty easy to understand. So
Okay.
definitely some reading involved that definitely want to look into a little bit more, but
Yeah, and
pretty self-explanatory, really.
it is. It is. It's not really all that difficult, and of course, I can easily say that because I've been doing this for over 40 years, and even longer as far as electronics information is concerned. But people who are it's a little foreign to them. But there's a lot of common sense here, and a lot of times you'll find in the question itself, the answer is kind of like there before you, and just kind of thinking about and kind of just plugging in your mind certain words and certain things that might jog your memory when you're doing the exam can go a long way. But the videos will be available for review, and I know you missed the first few minutes of it. I don't know what happened to the link. I sent it out 3 times, but once this is processed, once I stop the broadcast here and this is processed, I'll make the link available to the YouTube so you can finish it up. I see Mitch wasn't here tonight, and I do know that there are some um, Rich. He's a tech class ham. He was at the breakfast on Saturday morning. He is taking advantage. He's one of them taking advantage of these YouTube videos. So, at any rate,
There's
hey,
about the YouTube videos. I I don't know if you read all my emails, but
yeah. Did you not
uh,
get the links?
uh, I got the link for number 5, but
Okay.
when I put up the email, there was no link.
Oh, all right. I'll have to try. Let me see if I can do that. Send that out again. I'm going to stop the broadcast now. And if anybody needs to send me anything, any questions, again, the email address is wayne at n3lms.net. All right. Thanks for listening, everybody. I'm going to stop the broadcast.